Welcome to this particular lecture, and in this particular lecture we will see how to calculate the eigenvalues of the harmonic oscillator, the one-dimensional linear harmonic oscillator, right? So basically, I have told you in many classes uh, already that in quantum mechanics we have to solve for some particular potential, and we have to calculate the eigenvalues and eigenfunctions, right, for that particular potential. And that is just the simple business that we have in the quantum mechanics. We have some potential, right? We will write the Hamiltonian of that particular potential or particular problem, and then we will uh, think about some sort of trick, the mathematical trick, to get the eigenvalues and eigenfunction for that particular potential. So that is just the very simple and straightforward business. And now we are going to just do the calculation, right? The mathematical calculation for the eigenvalues of one-dimensional linear harmonic oscillator, right? And this is the topic that you have in your syllabus, which is called the matrix formulation of linear harmonic oscillator. So uh, in general, we have to solve the Schrodinger equation to get the eigenfunction and eigenvalues. But in this particular problem, we will derive, or we will see some new techniques, which is called ladder operator mechanism, or the matrix formulation, or the operator mechanism for the linear harmonic oscillator. So it's a beautiful mathematical technique to get the values, and it will give the same results as you will get the results after solving the linear differential equation, the Schrodinger equation. But this way, to get the solutions for eigenvalues, it is just very simple method in comparison to the solving of that two second order differential equation, the Schrodinger equation. That is much more difficult and cumbersome in comparison to this particular mechanism. So let me give you the glimpse, and let me give you the derivation. Right. So this is just the standard derivation. You will find this kind of derivation in any of the quantum mechanics book. You just can open the Griffith, Zettili, or any standard text on the quantum mechanics. You will find this particular mechanism, the step-by-step solution in that particular book. So if you are interested, you can go to the book directly. But let me show you the basic calculations. So first of all, to get the solution of some problem, we have to know the Hamiltonian of the problem. And you know, for harmonic oscillator, the Hamiltonian is the potential kinetic energy term, which is always the momentum divided by 2 times the mass. And the important thing in this particular problem is that we will use capital P for the momentum, the exact momentum, because we will define some operator with the small p. So just remember it. Plus the potential energy term, and in the harmonic oscillator problem, the potential energy term is half of mass times omega square into x square. But in quantum mechanics, we will replace x with the x operator, so it will be x operator square. So this is the Hamiltonian, right? So it is the Hamiltonian for the harmonic oscillator. And this is the Hamiltonian for which we have to get the solution. The one way we can get the solution is analytical method, which is an analytical method. I have told you that we can solve the differential equation. So analytical method is just the solution of differential equation. Right? So solution of Schrodinger time independent differential equation. So Schrodinger equation, right? So that is just the very pretty straightforward way, but it is mathematically very cumbersome, right? So we have found, or not we have found, but some physicists in the past have found that there is another mechanism, the mathematical technique, which is called the algebraic method. So it is algebraic method or matrix formulation or ladder operator mechanism, or in general the operator mechanism or operator method. So this is the second method to solve uh, for the eigenvalues of this particular Hamiltonian, which is the Hamiltonian for the linear harmonic oscillator. And this is the first simple straightforward way just to solve this Schrodinger equation. But in this particular derivation, we will use this second method to get the solution. So let me just start it. And it is just very straightforward mathematical technique. So you have to remember these steps. First thing is that we have to define uh, two new operators. So we are defining, or we have define two new dimensionless operators, right? The one is just the small p, right? So it is just small p, the new dimensionless operator, which is defined as the old linear momentum operator divided by square root of m h cross omega. So you have to remember that we are defining, so it's by definition, right? So this is just a definition that we are defining these new operators as the old linear momentum operator divided by this particular quantity. Now I'm saying that this particular small p operator is dimensionless, right? So the dimension of this particular quantity has to be the dimension of linear momentum, right? So let me just show you how the dimension of this particular quantity is just the dimension of harmonic, the dimension of linear momentum. So it is just very simple. It is m square root of m h cross omega, and h cross is just h h over 2 pi, and h is just the Planck constant, which is which the unit of this particular quantity you can get from E is equal to h nu, which is very famous Planck formula. So from there, the unit of h is the unit of energy divided by unit of energy, the frequency. So the unit of h is joule second. So you just can calculate from there. So the unit of h cross is just joule second. M is mass, so it is just kind of kg into joule second, and unit of omega is just 1 over second, because omega is omega, you know from your school physics that it is just d theta over dt, right? And theta is just the linear or two-dimensional angle, which is just dimensionless. So it is 1 over time, so it is just 1 over second, 1 over second. So second cancels to 1 over second, and it is just kg into joule, right? And joule can be written as Newton into the distance, Newton meter, right? So it is just Newton meter. So these are school physics. I'm not going to that detail, right? You must knew all that. So it is just Newton is just kg meter per second square, which is the force, the unit of force. So it is kg into kg meter per second square into meter, and it is just kg square meter square per second square, which is just kg meter per second. Kg is just mass, which is m, and meter per second is speed, which is or velocity, which is v, and m into v is just momentum, which is, we know that the unit of this particular denominator has to be the unit of momentum, and we just have shown that the unit of this particular quantity is just the unit of momentum, and that's why we are just saying that this newly defined operator is dimensionless operator, right? So I hope you got the idea why it is dimensionless. and we are defining one more operator, which is x operator. Again, small, sorry, not x, let me just call it p. Okay, sorry, q. So it is just the old operator for the coordinate into m omega over h cross. So this is the second defined operator. Again, this is unitless because the unit of this particular quantity is the is 1 over meter, and the unit of this particular quantity is meter. So it will be just the dimensionless operator. So you just have to verify the unit of this particular quantity will be 1 over meter, right? So this is an exercise for you to just be sure that the unit of this particular quantity is just dimensionless. There is no unit for this particular quantity. Now what we will do is that we will write the Hamiltonian in terms of these new operators, newly defined operators. Again, this is just a mathematical trick, right? And you will get the eigenvalues of the harmonic oscillator after this whole calculation. So the Hamiltonian in these newly defined operator will be, so you just have to replace for this particular p and this x. So it will be uh, this newly defined p, which is small p, into square root of m h cross into omega, the square of this particular quantity, over 2m plus half m omega square, and square of this particular quantity, which is q, over square root of m omega over h cross the square of this particular quantity, and it will be p square into m h cross omega divided by 2m, and plus half of m omega square divided by q square over m omega, and this h will be in numerator, so it will be h cross in the numerator. So just simplify it, it is just the basic mathematics. So it will be m, it will cancel in this particular expression, m will cancel in this particular expression as well. This omega, the power of omega, will be cancelled out, and in this particular expression we can take h cross omega over half as common. So it will be, the Hamiltonian will be h cross omega over 2 into p square, the small p square, the newly defined operator, and there it will be q square. So it is just q p square into q square. So this is the newly defined Hamiltonian in terms of newly defined operator, dimensionless operator. It is nice looking. Now it is just not the end of this particular problem. Now we are just starting to solve it. Now we will define two more new operators, right? Which are called lowering and raising operators. So we are defining a, the lowering operator, as 1 over square root of 2 into q plus, or yes, plus alpha p, and a dagger as 1 over square root of 2 q plus, or minus, sorry, alpha p. So these are newly defined, again the definition. So these are two new definitions, right? So as we were defining the dimensionless operator, we are defining these new two new operators. This one is called the lowering operator. So it is just and we will see in coming lectures why we are saying this particular operator as lowering operator and this particular operator as raising operator. So it is raising operator. So we will see why we are saying these two operators as lowering and raising. Now just calculate a very important quantity, which is just the product of these two operators. So we are now calculating a dagger into a. So it will be like 1 over square root of q minus iota p into 1 over square root of q plus iota p. So it will be 1 over 2, right, the product of these two terms, and q minus iota p into q plus iota p. Now the one thing that you have to remember in this particular calculation is that these are the operators, these are not the basic quantities. So in operators, right, you just have to remember that you cannot write these two terms as same. You have to know first whether these operators are commuting or not. If they are commuting, then you can write this way, but if they are non-commuting, then this equality will not hold. And that's why we have to remember when we are doing some sort of product among the operators. So it will be like 1 over 2, and you just have to calculate this particular product, which will be q square, and if you multiply this particular term with this term, it will be minus p square, but then it is iota square, which will be minus 1, then the whole thing will be plus p square, and plus if you multiply this term with this second term, it will be iota q into p, and this will be minus iota p into q. So it will be like half of q square plus p square, plus if you just take iota as common, it will be q into p minus p into q. And as I said that they will not be this particular thing will not be zero, because we don't know whether this particular quantity is equal to this quantity, right? If they are numbers, then this particular quantity will be zero, but if they are operator, then we have to calculate whether they commute or not. If they don't commute, then this particular quantity will not be zero, and we can write it like half of q square plus p square plus iota, and this is just the commutator of q and p, right? And we have to calculate this particular commutator, which we will calculate in a minute, right? So these are the important things. Right now we have to calculate this particular commutator relation or commutation. Now this particular commutation relation will be qp, and it will be like we can write this particular q by definition as x into square root of m omega over h cross, and this p as capital P divided by square root of m h cross omega. This is just by definition because we have defined these two operators as these two quantities. So it will be like x into square root of m omega over h cross into p over square root of m h cross omega minus p over square root of m h cross omega into x square root of m omega over h cross. and m into omega, the square root of m into omega, so it will cancel again. Okay, so it is just 1 over square root of h, and it is 1 over square root of h, so it is just 1 over h cross, so it is just like x into p, and 1 over h cross will be common because in this particular second term there will be just this particular quantity will be common. It is p into x, and if you are just familiar with the operators, then you must know that this is x into px, and this particular operator you must have calculated in your first unit, right? So it is just 1 over h cross, and we know, and even we can calculate. I'll show you if you don't know. We just can calculate it in the coming lecture, but let me just tell you that this particular commutation relation is iota h cross. So h cross will cancel to h cross, and this particular commutation relation, which is uh, q and p, is just iota. So it is just very important relation that we have calculated, because we have calculated the value of this particular quantity, which is iota. Now we can replace uh, for this particular quantity as iota. So this particular relation will be a dagger into a will be 1 over half or 1 over 2 h square plus p square. These are the dimensionless operator. It will be iota into iota, which will be minus 1. So the final result will be this product will be q square plus p square minus half, and you can just use this particular quantity to modify the Hamiltonian at this particular Hamiltonian, because you just can calculate the value of this particular quantity p square plus q square from this particular expression. So the value of p square plus q square will be like, or let me say the value of half p square plus q square, because that will be much more easier because of this particular factor of half. So it will be from this particular equation, the value of half of p square plus q square will be equal to uh, a dagger into a plus half, right? And you can replace this particular quantity, right, from this equation, and you can write the Hamiltonian. So the Hamiltonian will be equal to h cross omega into this particular quantity, which is a dagger into a plus half, and here a dagger into a is this n, which is called number operator. Again, there are many definitions of different operators, so we are defining several operator in this particular derivation. Initially we have defined these two dimensionless operators, then we have defined these raising and lowering operators, right? Now we are defining one more operator, which is called number operator, right? And we will just show in the coming lecture why this particular operator is number operator. But let me tell you just the final result, that this particular operator is number operator because when it will act on the energy eigenstate, it will just give a particular number, which is not a physical quantity, right? It is just some integer. Okay. Now you can just also verify that this particular operator, the number operator, is dimensionless operator, right? You can calculate the dimension of this particular quantity. Again, I have told you how to calculate the dimension, right? I have shown you how to calculate the dimension, so you can just verify by yourself that the dimension of this particular operator is just zero, or you can say this particular operator is dimensionless. Hence, the eigenvalues for this particular operator will be dimensionless. So the eigenvalues are just the numbers, and that's why we are calling this particular operator as number operator, right? So it is very important thing, right? So in terms of this number operator, how we can write the Hamiltonian? So the Hamiltonian will be h cross omega into n plus half. So this is uh, the new Hamiltonian, or just the same Hamiltonian, but we are just writing the same Hamiltonian in your way. Now, what we have to do, we just have to finally calculate the eigenvalues of the harmonic oscillator, and for that we will assume, right? Let us suppose that n are the eigen states of n, right? With eigenvalues, n. So how we can write the Schrodinger equation if we know that these n are the eigenstate of this capital N, which is the number operator with the eigenvalues this small n. So we can write like this capital N operated on these states is equal to n into n, right? This is again the assumption, and where this particular n are the eigenvalues of this operator, and they are just numbers, dimensionless numbers. Why? Because this number operator in itself is dimensionless. So this is the equation we can write, right? Now one more thing is that these n are also the eigenstates of H, and why they are the eigenstate of H as well, I will show you in the coming lecture. That or let me just say let me just show you from this particular equation, because H can be written in terms of n, right? So these two operator will commute, and if these if any two operator commute, then they have the simultaneous eigenstates. So if n are the eigenstates of the capital N operator, then these n will also be the eigenstate of H operator. So this is what the logic behind it, right? So these are just the eigenstates of H as well, and then we can write H acting on n will give you En, the energy eigenstate, because we know when this Hamiltonian operator will act on any state, it will give the energy of the system and the state itself. Now finally, let me write the result for this particular thing. So what you can do, you just can use these two equations. You just have to replace this H by this particular quantity. So it will be like H cross omega into n plus half acting on n will give you En into n, right? So you just have to operate this particular operator on this particular state, and it will give you H cross is just common, and if this particular operator will act on this particular state, it will give you n, right? Because if n will act on, or let me write it this way, n acting on n plus half, which is just in number, so it is not acting, it is just the multiply En into n. So it will be like H cross omega. When n will act on n, we have assumed that the eigenstate or eigenvalues are small n. So this particular uh, this particular term will give us n into the n states plus half into n is En into n states, and it will be like H cross omega n plus half into n state, which is just En into n. And from this particular state, you can just see that En will be equal to h cross omega n plus half, or you can write it like this, right? N plus half into h cross omega, and these are the eigenvalues, right? These are the eigenvalues of the Hamiltonian h, and this is what we have to calculate, and this is the final result, and these are the eigenvalues of harmonic oscillator, right? So this is it in this particular derivation. It is just a beautiful method to calculate the eigenvalues of the harmonic oscillator without solving the Schrodinger equation, right? So we need not to solve the Schrodinger equation to get the eigenvalues. This is the another way to use the operators, right? We have defined many operators. We have used the commutation relation and different things to get this particular expression. Even we can get the eigen functions by using the same mechanism, and in the coming lectures we will show how to calculate the eigen functions for the harmonic oscillator. Before that, we need to know how the raising and lowering operator will act on on these states. So that is again the basic calculation, right? But it is a lengthy calculation we will do in the coming lectures. But this is what is called the matrix formulation of linear harmonic oscillator, and this is the way how to calculate the eigen values for the harmonic oscillator. So thank you.